the question that you might just ask is about the invertibility of the matrix of change of basis. I mean, why the matrix is invertible. Perhaps you already could recall the argument, but let's go over it as we asked once. So we had a vector space V over some field F, and then we had two bases: V, the old basis, V dash, the new basis, and then we are going from one basis to another. So this was the old basis, and this was new basis. So if we are going from one base to another in this manner, so we are writing V as V dash V. That is, we are writing the elements of V in terms of V dash.
Yeah. So this is important that we just make sure that we are pre-multiplying or post-multiplying.
Which one?
Can you write V equals to P into V dash?
How we can?
He's asking if change of basis matrix is unique or something.
Change of basis matrix is different in this manner. So of course you could write it in whichever way you want to write. But the way we wrote it, was it not clear how we got this? And now, if instead of writing it the hypervector in this way, if you are writing it as column, then you could take the transpose and you will get the same thing. And then this goes on the left. But our convention is to write the basis as a hypervector in this form, like a row vector, because it makes it easier to write. So, yeah, man, up to this, was it alright for you? That is, this is nothing but expressing the elements of V in terms of V dash. Okay, fine. Note that exactly in a similar manner, we could also write V dash as B Q, right? For some other matrix, an n percent matrix Q. Now, the columns of this matrix are the linear coefficients or coefficients of the linear relations, not linear relation, linear combinations of the elements in V, which are expressing the elements of V dash. Exactly in similar manner as we did here, expressing the old basis in terms of the new basis. Here we are expressing the new basis in terms of the old basis. It's doable, right? Now, note that since V dash is equal to VQ, well, we actually wrote these brackets just to say that these are the hypervectors. So we wrote something like this. It's fine. I mean, you can do without them if it is clear what you are trying to say. Otherwise, this is a little clear notation to say that these are hypervectors. And then we replaced this bracket B, this hypervector whose elements are the elements of the basis B, by this. Okay. So B dash B, sorry, B dash B Q. So we were representing the elements of the basis P dash like by B dash PQ. PQ is, this is an n cross n matrix, this is an n cross n matrix. As a product, you are getting some matrix which is representing the elements of B dash. So for example, if you consider the ith element here, say VR prime, well, let's write it down here, that V is V1 order Vn and V prime is V1 prime order Vn prime. Okay. So this Vi prime then is equal to C1. Okay. Now we are considering what? The ith column of this as well. That the ith column here would give a linear combination of the elements of V prime, that is V1 prime to Vn prime, which will give this ith element in V prime. Right. So we are having, so let its ith column be C1 over C1. Then Vi becomes C1 C1 V1 prime plus dot 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 Cn Vn prime. Right. So you are expressing the elements of V prime in terms of the other elements of V prime. Now, is this possible? I mean, if this is the case, what is the coefficient of Ci? And what are the other coefficients? Can you tell me? Yes? Yes, this is the ith column of this matrix PQ. And then this Vi prime, which you have here, what is bracket V? This one is nothing but V1 prime, V2 prime, dot dot dot, Vn prime. Right? So we are taking the ith element here, which should be given by the ith linear combination, which we get from here. So once we have this, what can you tell about the coefficients?
They're all zeros except the Ci.
Wonderful. Yes.
So just a couple of zeros and the one in the ith.
Alright.
Because they're linearly independent.
Your name again?
Ridhiman.
Ridhiman. Thank you, Ridhiman. Yes, because these are all linearly independent. Ma'am, are you following? So since these are all linearly independent, unless they are all zero except the ith one, you are getting a non-trivial linear relation among them. Okay? So this one would immediately imply that Ci is equal to 1 and Cj is equal to 0 for all j not equal to I. So then what can you tell about PQ?
It's identical.
It's the identity matrix. Right? Similarly, instead of replacing B here with B dash P, if you replace B dash with BQ here, you will get that QP is also equal to identity. So Q is anyway the inverse of P. In particular, this matrix of tensor places are inverse. So this implies PQ is identity. Similarly, QP is also equal to identity. Okay?
Sir,
Yeah.
so couldn't we have concluded that right from the second
Of course,
question,
yes.
right?
But I'm just saying that it's quite similar. I mean, if we have PQ identity here, just a similar argument on the other side also implies that QP is equal to
No,
identity.
I don't mean that. I mean that B dash is equals to B dash PQ. From
Yes.
there, can't we directly write the PQ?
Sure. If you remember that basis, I mean elements. So every vector is uniquely expressible as basis elements. From there you can directly write that this is identity. So I have not skipped any steps so that I can understand everything that we have done. So
Can you explain that argument again?
which one? Here? So this linear relation, what does it imply about the coefficients? We have this ith column, and now we are having Vi prime is equal to C1 P1 prime dot dot Cn Pn prime. What can you tell from this about the coefficients C1 to Cn?
How will you see I is equals to 1 and others?
Because and why?
As since the elements of the basis should be linearly independent.
Wonderful. Yes. So that was the argument. So this in particular implies that P, Q both are elements of GLN F. Okay. Both are invertible. So I hope that answers Mark's question. Note that in particular this argument also implies this. That is, let B be a basis of B, then every other basis of B of B is given by the relation, well, every other basis give that a name, so that's an arbitrary basis. B prime of B is given by the relation B dash is equal to BC or the other way, it doesn't matter. Because what I'm saying that you are given a basis, multiply it with some element of GLNF, and you get another basis. And for every other basis, you will also get such a thing. So for P in GLNF, if
So
yes,
it holds for any member of GLN.
this holds for
Any member of GLN.
it holds for any member of GLN, because I mean, so we have seen one way, right? That is, if you are given two bases, you can express another with just, I mean, so if you are given B and B prime, there exists a matrix of change of bases which represents your new basis or your old basis in this way. So you can go from one basis to another by multiplying with the matrix of change of basis. Now, I guess your question is that given any element in GLNF, if we multiply our basis with that thing, whether we are getting a basis. Let's check. So that's the only thing that we should do for proving this proposition. Okay? So suppose we are given this basis B, and then we are getting some set of vectors B prime. So let B prime be such that B prime is equal to B P for some matrix P in GLNF. So you are taking a matrix. Okay, I should rewrite this first line. Sorry. So at first we should take some P in GLNF. Let P be an element of GLNF, and we are given B, right? Now let B prime be such that B prime is being defined by this equation. Okay? All you have to show is that the elements of B prime are linearly independent. So suppose they are not. Because
to show
no,
this span B also.
What?
Won't we have to show that this span B?
No, because once you show that they are linearly independent, they will be
exactly
exactly
the same cardinality.
So suppose, in fact, it's rather easy to show that they are spanning B. So you can show either way. I mean, you can show that they are either linearly independent or they are spanning B, because there is P, right? So every linear combination of B, you could so let's show that they span B. That will also do, right? Because there are n elements, they're spanning the entire set. So instead of showing linear independence, we could also show that they're spanning B. And since there are n elements there, they should be forming a basis.
So, but in the proposition we haven't said that the dimension of B is n.
What?
In proposition we haven't mentioned that the
What? What did you mention?
no,
Yeah, if V is finite, then we have no problem, right?
V is
Finite, we have no problem.
V is finite, will say? Oh, finite dimension. Yeah, sure. Because I mean, till now, everything we are doing are on finite dimension spaces. We will be considering only finite dimension vector spaces. Thank you for mentioning that. So basis B prime of finite dimensional vector space. Okay. This will be implied in all our propositions unless explicitly mentioned. Okay. And we are generally not working with infinite dimensional vector spaces, as you mentioned. Only that if you are having an infinite set of vectors, the span of this would be a finite linear combination. That is, you will take finite number of elements from that at a time, and you will take all the linear combinations of them. That will form a span. But we are not going to work with it, at least in this course. So Vikram, in other words, whenever we write a vector space, we will mean that dimension is finite. So B is V1 to Bn, and B prime, say, is again V1 prime dot Bn prime. Okay? Then these relations star implies that some vi prime are just some linear combination c1 v1 plus dot 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 cn vn, where c1 dot 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 cn is the ith column of p, as we just did here on the right. Where this is the ith column of p. What are we going to show? That v prime, the elements of v prime are also spanning the set. Okay? And this will follow from the invertibility of p. So just think for yourself why. How are we getting that this is a spanning set of p from the invertibility of p?
If say one of them spans V.
Yes, v spans p, we know, because it's a basis. So that means any vector v is expressible as a linear combination of p. I'm just writing that. Rest to think.
Actually, when you multiply it by the matrix V and
But yes, by the inverse of x, and we are done. So we are going to show, or we show, spans V. Let V in V be an arbitrary vector. Let V in V be an arbitrary vector, then V, we could write this as C1, or okay, just 1 minute, some A, because we have already used C.
D1.
A1, B1 plus dot 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 plus AN, BN for some A1 dot dot AN in Fn. Right? This is the coordinate of this is the coordinate vector of V in Fn. Right? So that in particular implies that V is equal to B times this A1 dot 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 AN. Right? Okay. Now recall that we have this B dash is equal to BP. Let's multiply with this, the inverse of B on from the right. So that means what we get from there, B dash is equal to BP. That implies B is equal to B dash P inverse, right? Okay, so we will just plug it in here instead of B. B dash and B1 dot dot in here. Okay. The same vector goes here, and this B is replaced with B dash P inverse. Alright? Is this fine for all? Ganesh? It's not? Okay, where are you stuck? Which one? Here? Here. Okay. So we are having an arbitrary vector V in V. And you know that V is a basis of it, it's given. That means that arbitrary vector V is expressible as a linear combination of your basis vectors. V1 to Vn are the basis vectors, so you should have written it down somewhere here. Yeah. We already wrote it down that V is this table of vectors. Okay. So that means this arbitrary vector has could be expressed as a unique linear combination of the elements V1, V2 to Vn. Okay. You are writing it down here. This is a unique linear combination. And then you are writing it in this manner. That is, this is what we wrote here. This one is nothing but writing this as this hypervector v1, v2 to vn times a1 dot 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 an. Is this alright? So this one times this one is giving you this one, right? And this one we write it as also this one, okay? B square brackets on both sides. So it's still this one. Now how we come from here to here? Just using this equation. Yeah. Because we have that we wrote the same thing here. B dash is equal to BP. Okay. And now we know that this is invertible. That was a question of mine at first. That is why this is invertible. We explained it a few minutes ago. So we are multiplying with the inverse of this from right. So that means this one vanishes, right? P times P inverse, that becomes I into P. So you are getting just B here. And on the left hand side, you are getting B dash P inverse. So we just put it here. Till now, it's clear. Is this clear to all of you? Yeah? Okay, so Kaushik, are you alright with this? So tell me now what we are going to do after this. Yes, it's already complete. I'm just asking Kaushik how is it complete? Well, we have written that this is P inverse times this. You multiply this. What do you get? A vector. Some other vector. V1, V2, Pn.
1 by.
Yes. Right. So you are getting. Sorry. This is B prime times some V1 dot 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 Bn for some other V1, V2, Bn here, which are equal to. I mean, what is the relation of that with this matrix and that vector? Here we are just having that V1 dot 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 Bn is equal to P inverse times A1 dot 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 A. So we are multiplying this two and we are getting this. Now what does it mean? That V is expressible as a linear combination of the elements of B prime. Right? Raj, is fine? Okay.
Won't you have to mention that that BI are not all equal to 0?
Which ones? It doesn't matter. You are writing here V. Yeah. All we declare is that this spans. Because if we have a spanning set of coordinate n which is spanning V, then it is going to be linearly independent because B is the coordinate of B prime and B are the same. So thus we show that indeed B prime spans V. So done here. It's clear to all of you? Devangsh is here. Yeah, Devangsh. So is this point clear to you? By the way, please change your questions. Thank you. I mean the questions, both of which you mentioned in the write-up, are propositions from the previous class. So that's not allowed. And Rotmandeep. Where is Rotmandeep? Yeah, you actually overdid it, but one or two questions are fine, but you wrote 6 of them. It's very good that you thought about so many nice questions. But nevertheless, all of them are nice, so we are keeping it. And once you send the corrected version, we'll upload it. So, where were we? We are done with this provision, right? That is B dash. We have just showed that such a thing which you get after multiplying. Please a bit quiet. So, if you are at first given 2 bases, we can go from one to another by the matrix of change of bases. Also, if we are given a basis and we multiply it with some element of GLNF, we are getting another basis. We have just shown that. So in other words, you get bijection between the set of bases of a vector space on n-dimensional vector space on one hand and GLNF on one hand. How does it work? Please tell me. So you are given a vector space with some bases, and start from there and tell me what is the bijection that you have with GLNF. the set of invertible matrices.
B is equal to P prime.
Bp is equal to B prime. You have this. I mean, all you have is
We
this
have
function.
one basis,
Yeah.
and we have to show a bijection between the set of all bases and the set this GL and F.
Right. Yeah.
So we can, to every basis we can assign the matrix P belonging to GL and F such that B prime is equal to the given basis into P.
Right. Yes. Fine.
Can't we just show that let's say we have a set S of all the bases
Yes.
and that is equal to GL and F, because like say if you
No, the set of all bases is not equal to GLNF.
no,
I mean, if you are talking about
change of basis,
change of basis.
Changes.
Yes. Right.
not basis.
Well, actually, that is also already given by this, right? That is
Yes.
the change of all the change of basis matrices are coming from GLNF, and those are the only change of basis.
So if there is a like if two sets are equal, there is a bijection from a set to itself, right?
If two sets are equal, which two sets now you are talking about?
The set of all change of basis matrix.
Can this be y? For a fact. So now we are writing down a corollary. Corollary 1 that exists bijection between. So the set of bases of between, well, V is some finite dimensional vector space over some field A, and I should not write it here. It's implied. We are carrying it from the previous portion. Okay, it's a corollary of the previous portion. So here all we want to write is that there is a bijection between the bases of V and GLN F. Okay. Where of course we are assuming that V is a vector space over F, and this N is the dimension of V. Okay, dimension is not legible. Yes. All right.
So, can we take a function from GLNF to the set of all bases of V such that we such that P
So give the function. So you are given the basis, and you are given the vector space V, and you may assume that you are also having a basis. Of course, you have to show that there is a correspondence. I mean, there is some element in GLNF which corresponds to that element as well. But you can start with the vector space V and some basis of it, and then proceed.
and then we'll say that from the GLNF we use that GLNF to transform one basis into another basis.
One basis into another basis.
Basis, and like then we have two cases. If there's either the identity matrix itself,
A
which
bit
will
quiet.
just
A bit quiet.
this is the identity matrix itself that will convert the basis into itself only.
Yes.
And then there are other bases which are unique because the P inverse will be different from P, and
Sure.
so and that's why, because they're unique and there is a unique correspondence with every element, then we can we can say it's bijective.
Sure.
And
So-
I think that will prove the injective part.
Yeah, actually it proves both, right? From GLNF you are starting,
Yes.
and you are getting every basis of V.
Yes.
Well, and then you have to just say that it's surjective. I mean, that is given any basis, you get a matrix of change of basis, that will be here.
Yeah.
Very good. What's your name?
Somna.
Sean. Thank you. Yes, Fahmi, you want to say?
Yeah. So we have to just prove that the change of basis matrix between any two bases is unique, right? Then we are done.
It's unique. We know that it's unique.
But aren't then we done, because like to every two bases there is corresponding a single change of basis matrix.
Okay, for any two bases, that corresponds to change
And
of
every
basis.
change
Because
of
every vector is expressible as a unique linear
Yes.
combination of any given basis.
and every change of basis matrix is in GLNF.
Right.
And we have shown that every member of GLNF is a change of basis matrix.
Right.
So aren't
Yeah, we are done. We are of course done. So please tell me if this already is clear to all of you. I mean, we got the argument from Shaunak and Falgun, but this argument should come from each of you. So if any of you are having trouble seeing this, I mean, how this already follows from this proposition, please let me know.
How can we show that for every decimal P is unique?
P is unique because you know that I mean, given a basis, there is any arbitrary vector V is expressible as a unique linear combination of the elements of that basis. Right? So if you are given a basis B prime and a basis B, you know that the change of basis matrix is then, well, we saw that the old basis is written as B prime B. Now, what are the elements of B? These are the linear combinations of these which are expressing this. So every column given B and B prime, every column of P is uniquely defined. So P is
So how did we prove it's injective again?
which one?
There.
The
We have
basis
to
of
prove that
so,
it's bijective. So objective I got. How is injective?
okay. So otherwise, two bases would, well, two GLN and two elements of GLNF would give you the same basis.
Right.
Okay. So let's see that. Is that possible at all? Okay. Shona, actually you started with this thing, so you should be able to give.
So one way to show an injection is that if we are defining from the basis of V to GL and FF, then if we take two unequal elements in the general linear space, and their pre-images should also be unequal.
Which one? So you are taking some P and Q in GLN.
P and Q are not equal,
Unequal.
and so the basis matched to them, they should not be equal.
The basis.
The basis with which each of them is matched.
So you are getting BP and BQ.
Yeah, BP is not equal to BP.
And her question is why?
Because P and Q are not equal, so the reference basis into P and the reference basis into Q, they won't be equal.
Okay,
So
you can
BP
also say
and
that
BQ.
if BP is equal to BQ, then take the inverse of one of them. Say BP is equal to BQ, so you can write B as B times PQ inverse, right?
BP is equal to BQ.
BP is equal to BQ. Okay, we can use this. Suppose BP is equal to BQ. Inverted. Multiplied here. And here you get B is equal to BPQ inverse. What can you tell about PQ inverse then?
Then it is identical.
And that means Q and P has to be the same.
Yes.
PQ inverse is it clear, Shama? Srinivas.
Yes, sir.
So
Right.
yeah, it's better if you ask your questions here.
I got it. I got it.
So
I was just asking, can't we multiply B inverse on both sides?
yeah, of course. You can use Q inverse or P inverse, whichever you wish.
Right.
But you get then QP inverse is identity.
Yeah.
That again says that P and Q are the same.
P and Q is got it.
Yeah. Yes. Okay. So this already is clear to all of you. You, what's your name, please? Yeah. Anuma? Okay. So you are in a previous group, right? You have already typed. Yeah. So I just wanted to know whether this is clear to you because in the entire class I saw only you sleeping. So please tell me if you are stuck, we can discuss it again. So that the basis of V and GL and F, there is a bijective correspondence. The argument we just gave here was, did you get any part of it, or if you have any doubts, you can again explain. Please. Yeah. Okay. All right. So this will help us now to answer the question with which we started the earlier class. That is, we wanted to get the dimension of J to F. J to F. Dimension, not the dimension, the number of elements in J to F. Right? So let's clear this board up and determine the elements in GL2. Even before going to GL2FP, how about GL1F? How many elements are there in GL1F? One?
The perfect way.
Okay. GL1F. The coordinate of this.
How you said one element?
Yeah, Yavi.
1 plus 1 is equal
Yes.
to many.
What?
1, 2, so on.
Which one? This one?
It can be 1,
Okay.
it can be 2,
The
and so
function?
on.
Well, it's a correspondence. You could tell also a function. It's a function. You are starting with the certain base B. And then this B, you are mapping and you are taking B prime is B. Okay. So every element here in GLNF, that is P, is being mapped to this basis. B prime. In particular, note that if you are starting with this basis P, then you also have an element here that is, because B is a basis, you should send some matrix there to that basis as well, right? And that should be the identity matrix. If you replace P with the identity matrix, you get B itself here. Okay? So this way you are getting all the bases of V here, starting with the matrices from so that was the map. And then we showed that it is injective, it is surjective, and we are done.
So we are only concerned with existence, right?
Yeah.
We can't necessarily state a function that has like is a bijective.
Well, here the function, I mean, if this is this, then we say that f of p is equal to b dash. If this happens, so that is the function. So we have indeed a function from here, and then we showed that this is injective and surjectivity also follows from the previous function. So we're done. Yeah. Base B. No, this is just a hypervector, and then you need to have some element here which should be mapped to B itself, and that matrix will be the identity matrix. Because B times the identity matrix will give you the hypervector, which is the hypervector of B itself. And all the elements are uniquely expressible. So identity is the only matrix multiplying B with which we are getting B itself. So now let's come back here. What is GL1FP, the coordinate of that? Yeah.
Same as cardinality of F.
Are you sure? Coordinate of F?
FP.
Coordinate of FP. So the question mark is whether this is true. I mean, is this right?
Coordinate of fp minus the 0 element.
Yes, we should remove 0, right? Because 0 is not invertible. Right. So this is coordinate of FP minus 1. And do you know what is the coordinate of this?
Of what?
Of FP? P, right? So we could just write here P minus 1. Alright? So that's it.
Sir, how is the cardinality of FPP?
That's how it's defined.
There are B elements.
How are you defining FP? Please tell me.
How are you defining FP? Oh, right.
It is where it's not P is it, right?
Right.
So the residue classes are from 0 to P minus 1. So GL2 FP, GL1 FP is done. How about this?
Yeah, that's a little
P
bit
square minus 1.
Yes?
P square minus 1.
P square minus 1? Okay,
P
let
for
me write it down.
P for 4 or P square?
Is that true?
P for 4 or P square?
I was just
P by
asking
4.
for my induction, sir.
P by 4.
P for 4 minus 1?
Yes, sir.
Honestly, I was just for my induction.
Again, is this true?
Well,
No, it is not.
there are a lot of.
I know it is not.
There might be. We have to subtract the configurations
So,
that conform.
yeah,
to-
how do you start it? We said that we use this already. So, think of this. What do you have to do?
You have to find the basis of FP.
The number of bases of
A number of bases.
bases of
FP.
FP?
No, of any vector vector space
Of
over
a
FP.
two-dimensional vector
Two-dimensional
space.
Right.
vectors in it.
Have you an example of a two-dimensional vector space over FP?
F to the power 2, I mean,
FP squared.
F squared.
So this is of course equal to the number of bases
Minus one.
in FP, or number of bases of FP. So all you have to figure out is how many bases are there, how many different bases you could get in FP. That's an easy task. So how many elements should be in the basis of FP2? FP squared. Two elements, right? Because it's two-dimensional. Or the one standard basis is just the columns of the arguments. Right? So all you have to figure out is how many linearly independent pair of two vectors you could have in FP2.
So like the total number of combinations we can make from FP is like P into P minus 1.
P into. So you are trying to get something like A, B, C, D, all the entries from FP, and so this says that A, B, C, D are in FP, and these two things are linearly independent. A, B, and C, D are linearly independent. So let's count them one after one. How many ways to choose AB? The first vector. Yeah?
But we
square.
have to account for like when A and B are equal.
And both are
So
zero.
P square minus 1.
P square minus
But
P.
P.
This
Why
one
can't
is-
both of them be equal?
So there'll be like an
Right.
2, 2 and 2,
Yes,
2 will be
got
counted
it.
twice.
Yes, got it.
Yeah, but it's still a different basis, right? So if what I want to say is that AB, all you have to choose is well, what you have to choose. That is the number of elements here, the number of vectors, which are linearly independent. I mean, what one-dimensional vectors are linearly independent? What are they?
1, 0 and 0, 1.
If you are given one vector, that set is linearly independent when?
When it's
C1, 0, C2.
When it's not zero. So how many things you have to throw away then? From
Two things. So both
square
of them,
minus one.
right?
p square minus 1. Yes, exactly. In p square minus 1 ways, you can choose the first vector which is non-zero, that is, which is linearly independent. I mean, yeah. Only this thing, A, B, C, D, a choice of A, B, and C, D, will not be linearly independent if, I mean, when you are just choosing one element, if you are choosing a zero thing here. Because everything else depends on the choice of the second vector. But if you allow a zero vector here, then this set cannot be linearly independent. So all you have to care while choosing the first vector is that this should not be zero.
But aren't the cases where like first we choose AB, then we choose CD?
Yes, right?
So, but aren't the cases where A is equal to B are being counted twice when we choose C?
We don't care now. All we are caring is about choosing the first vector, and we would choose it in such a way that the set is linearly independent. So unless you plug in a zero vector at the choice of the first one, then your set can still be linearly independent. So even if A and B are the same, what I want to say is that so 1, 1 here, and
And the set will be different.
the set will be different, right? Yeah. So again, then in how many ways we can choose AB? Don't. I mean, I'm not asking an answer from here, whom we just discussed, but from the rest of the people. Yes, Jamini, you want to say? Very good. P square minus 1. So this, let me write it down somewhere. Yeah. AB can be chosen, or we can choose AB. In P square minus 1, giving off 0. Now, how many choices for CD? What CD is allowed to be? I mean, you have already chosen it.
It's not allowed to be the
It's not
multiple
allowed to be
scalar
zero,
multiple of it.
Right. So, how many you should throw away now?
NP.
Yeah.
P square
My
minus
NP,
1 minus
N square P square.
For any one combination,
No,
you
wait.
take all the other combinations.
Yes.
For any one combination, you take other combinations and then sum it.
So now you are forgetting about the choice of AB. You are given AB. You have chosen some AB which is non-zero in P square minus 1 ways. Now you are choosing just CD.
Then all the other choices, that is, we have already taken two.
P
Yes
square.
or maybe. Orko?
Should we remove all the scalar multiple sets as P elements, so we remove P such elements?
Right. So how many choices then?
P square minus 1 minus
P square minus?
1 minus P.
Why you are subtracting P minus 1 elements? Or P plus 1 elements actually?
Because CD, if we choose CD independently, it could be chosen in P square minus 1.
You are not choosing CD independent. I mean, the choice of CD is depending on the choice of AB. So we are given AB.
Now we impose the restriction that P such elements like P scalar multiples of these kinds.
Yes, so
We remove P.
okay. So how many choices? Given AB?
P square minus 2.
P square minus P minus 1 again. How many choices?
There are P scalars, so there are P scalar multiple.
Yes.
Since there are P scalars, there should be P scalar multiple.
Right. So what should be the choices?
P square minus P minus 1.
Into, right?
P square minus P minus 1. Why?
Why are we-
It's not the right answer.
So shouldn't it be just one
Can
way?
you leave this as an exercise?
See,
No,
No, wait.
no.
we can leave the hard things for exercise. Actually,
No,
it is the last question in the set of exercises.
So for every P square minus 1 ways, we can choose the CD in P ways. Right?
CD in P
No,
ways, right?
not P ways.
Yeah, even if you can
Like
choose
leaving
CD.
out P ways. So we should be multiplying that, not subtracting.
Okay, so what I want to say is that this can be chosen in P square minus P 1 ways. And then we of course need to multiply it with something for the choice of CD. But now the question is that given the choice of AB, in how many ways you can choose CD? So suppose you have some CD, or some AB, say 0, 1, 1 is the choice of the first one. You have this one. How many you should throw away?
One.
P.
Then we only throw away one.
Well, to start with,
This
we have
is-
to
this
throw
is
away
your
zero,
ABC.
zero.
You'll have P scalar multiples, right?
Right. So how many you should? So this is equal to this. Okay. Suppose we are having this as a choice. This is one of the choices. One of the P square minus 1 choices. Then how many we should throw away?
To start with, we have to throw away 0, 0.
All right. So then how many choices for CD is left? I mean, even this choice.
P square minus P minus
Minus 1. Why P square minus P minus 1? Everybody is saying that, but why?
No,
P, so why you choose CD in only one way?
What?
CD can be chosen in only one way.
Why?
Because any other way it would be linearly dependent.
Any other way? So how many? So,
Three.
suppose you don't
What
have
are you
any.
talking about?
Don't have any
2, 3, 3, 4, 4, 5.
Wait,
I
wait,
don't know,
Sean.
man.
Let's reverse it. That is, you are going to choose AB in how many ways?
P square minus 1.
P square minus
1.
1 ways, right? Now for each choice of AB, how many ways? In how many ways you can get CD?
Our period mode 0 is included, right? So you're just gonna make P square minus, no, not P square minus P.
P square minus P. Yes.
Why is everybody
Why everybody is saying P square minus P minus 1?
I don't
How do you get that extra 1?
Because we still have to throw 0.
What?
No, that is
Why?
Period mode is
You are
0
already
is
throwing
included.
away
You can multiply.
zero. How many
1,
elements
1,
are
0,
there?
0 is invertible.
What?
Is 1, 1, 1, 0, 0 is not invertible.
1 1 0 0?
It's not invertible.
Yes, we are throwing it away, right? If you are having 1 1 and we are removing P multiples of it, what are those? It is the P multiples of
0, 0 is a multiple of everything.
And then 1 1, then 2 2, and so on. This goes on up to P minus 1 minus 2. Well, all modulo P.
All of you are confused, you're confusing me.
So then, the number of ways. See? Can I work this part out?
So it's gonna be P square minus 1 into P square minus P.
Now even
We should have solved this before.
AB, we may choose CD in P square minus P ways. So that gives now the cardinality of, well, the number of bases of FP is now what? The product of these two, right? So you have P square minus 1 times P square minus P.
So for general case, it will be Pn minus 1 into Pn minus P,
Well,
right?
I'm not saying, but okay, let's at least do one more case. Or I mean, how much time is left? It's just 5 minutes. At least discuss what happens for GL3P. So for GL3P, again, there will be ABC, DEF, and some other. So 3 tuples of vectors you should choose. How many ways you can choose the first one? Now we are considering this. FP3 instead, okay? Not FP2. So we are trying to get all the number of bases for FP3. So the first vector for the first choice, how many are there? P cube minus 1. Yeah, right. The second one?
P cube minus P.
P cube minus P. For the third one?
This is very good.
P cube minus again?
We have to subtract scalar multiples of 1, scalar multiples of the second row, scalar multiples of the combination of the first one and second.
Okay. Is in the first two sets that you said, that is scalar multiples of the first one and scalar multiple of the second one, is not contained in the last set that you mentioned, that is linear combination of them?
Oh my god.
It is, because it is multiplying it with some scalar and adding 0 times the other one with that. Right? So it is actually the set of all linear combinations that you should remove. In how many ways you can take linear combination of 2 n ways?
P square.
P squared. So how many things you should remove?
P square minus.
P cube minus P cube minus P squared. You are done. So you could actually now give the argument for GL and FP, right?
Can we
So this is, yeah.
can we forward this argument by induction?
Actually, it's much easier to do it directly, right? Easier to do it directly using the coordinate. So is it clear to all of you how we thought even about this problem for GL3? GL3, is it alright for all of you? Okay. If not, just let me know or let your tutor know and we can explain again. That's all for today's class. Louder, louder. A bit quiet. We have one more question. Yeah. Of these two things, the first two.